Hold on. Okay. As per usual, it's Wednesday. On Monday, your Alex is due. It does look like some portion of those are going to come out. I don't know how many. Somewhere between 2 and 4, 2 and 6. You can expect the bonus points quiz and the Chem and Life to be graded by the start of class on Monday. When they are all graded, I will unlock those. I don't envision it will take forever. Mostly it's that I need to sit down and look at all of them. So that should happen. I know in class on Wednesday, no, today is Wednesday. On Monday, someone asked, like, this isn't going to affect my grade. I do want to be real clear. It's possible that I've set it up to the best of my ability. If somehow it's giving weird numbers, like it's making your grade go down, I'm going to fix that. I just won't know until I unlock it, and then I look at the grades and watch them either go this or this way. And I know that sounds terrible, but it's that or I unlock one of you at a time and I have to send you an email that's like, hi, I'm playing with your grade, please don't panic. And I don't know your alert system, so I should probably not be doing that. But that's what that is. On Monday, we have a mini exam. It's mini exam 4. It includes Tesla's law, pizza formation, light, energy of a photon, the calculation of energy for electron transitions, which we will finish talking about today. It will go all the way through 6.3. So in chapter 6, there's 4 sections. We are finishing all of the 3rd section today. It's quantum numbers. As a point of reference, the last data withdrawal from fall courses is November 12th at 5 p.m., which is in 2 weeks. I think, yes, give or take. I don't really know about dates anymore. I kind of know that today's the end of October. This weekend is Halloween in Florida, Georgia. Please make adult decisions. You will get a 0 on your mini exam if you are in jail on Monday. It's never happened. I don't want it to happen this year either. Just to be clear, I want you to make grown-up choices. Please use Uber or Lyft if you need to. Questions about announcements, other topics, I don't want to say life issues, any other complications? No. Y'all are exceptionally quiet as per usual. And on Monday, I will bring a picture of my dog in her Halloween costume, just to bring you all a little bit of joy. She has one costume. She's worn it for 10 years. And every year, she gives me the same look of like, I hated it then and I hate it now. And I don't.
So like how you said, like you just won't get to like all the algebra practices. So like basically we'll do just like both of them, so then like they'll just be like class 2 for us.
Yes. So the questions that Alex objectives. So on Wednesdays, I go upstairs, I hit post to YouTube for the video, because that takes like 92 million years. And then while that's loading and I make sure everything else is done, I go into Alex and move them out. So in theory, depending on how long it takes me to get out of here, it should be done by 6. But it is done before I leave, which is usually by 7. But it will be done by the time I go to bed tonight. And that's my assurance in this life. It should be as soon as I get back to my office. I did not have Wi-Fi on that computer because I refuse to download whatever that is to get Wi-Fi on my computer. That's my own personal decision. Please don't make it. That's my life choice. It's dumb, but it is my choice. So, other questions? My God, could they ever fix the AC in here? I mean, the answer is no. We're all going to sweat. It'll be fine. Sorry, video people. It's going to be extra bad today because I need the whole board. So, glad you're all here today because I'm going to basically go from here to there and everything else. Oh, I remember the other thing. The SI, so Mahi in the other lecture mentioned there was a survey. The Friday session is moving to Zoom. Same time, new place. your computer wherever you are. So, back. I knew I had something else I needed to tell you. She said she's going to send some information about all of that. However she usually does it, but I'm not copied on those, so that's all the information I have. So on Monday, we drew this diagram, which is the energy states really coming from the Bohr model, where we have n equals 1, 2, 3, 4, 5, 6, and they're in increasing order away from the nucleus, which we haven't really identified, but is basically at the bottom of this graph. And so in this case, we have these different states. Between the Schrdingers Equation and Bohr's hypothesis, he was able to determine what he thinks or feels any of these states are energetically. And so there's a couple of things we're going to think about. So delta E, in this case, which is the change in energy states, is negative 2.18 times 10 to the negative 18 joules, 1 over n f squared minus 1 over n I squared. So a couple of things in this equation. So Bohr determined that Planck's constant times the speed of light times the Rydberg constant gives you 2.18 times 10 to the 2.18 times 10 to the negative 18 joules. You can multiply all three of those values in your calculator every time, or you can use this other version. Both versions of this equation will be on your constant sheet. You just can do more math or less math. I like less math. I like a good constant. So that is where those numbers come from. And so when delta E is positive, NF is greater than NI, and the electron absorbs energy with E photon equal to delta E, where E photon equals Planck's constant times the frequency. So if delta E is positive, the final is greater than the initial. It's going to go up in the graph because we're going to start looking at calculations. Alternatively, if delta E is negative, NF is less than NI, the electron emits energy as light with an energy E photon, EPH, is equal to negative delta E. The change in energy is a finite number. The wavelength of light, so the way this works is we have an electron here, in the n equals 1. If you hit it with a laser, the photon of light basically bangs the electron into a greater energy state. So it's going to absorb that energy and transition up. That energy corresponds to the wavelength of the light that hit it. If it is up here and it decays, if it goes from n equals 4 to n equals 1, when it decays, it gives off light. That light has a wavelength that corresponds directly to the change in energy. But it is the negative change of energy, so negative delta E. We're going to do 2 examples. This will hopefully come mildly full circle, but it's possible. So these are just not standards, but this helps us think about this in terms of where we're going. So in this case, we can start to calculate the change in energy. So in this graphic on the board, you have a transition diagram where we have a blue line that starts at the n equals 3 state, where no point, and it ends at the n equals 1. All states are shown. If the n equals 1 is the bottom state, You just count up by whole numbers. 1, 2, 3. You could count all the way to infinity. That would be a waste of our time. It's usually less than 6. Typically, so this graphic is not perfect, because I clearly made it myself. They should decay in energy by halves as you increasingly look at these. So as the energy states get higher in number, they do become closer together. So in this case, it says an electron is excited by a laser and completes the transition shown on the right. What is the wavelength of light for this transition in nanometers? So in order to do this, we need to calculate the change in energy. And then we need to remember that the change in energy is related to the energy of a photon. The energy of a photon is equal to Planck's constant times the frequency. I promise this will all maybe make sense after we do an example. Maybe not. No, it should. So in this case, we know that NF equals 1, NI equals 3. That value came off of this table up here. So we know that delta E equals negative 2.18 times 10 to the negative 18, 1 over NF squared minus 1 over NI squared. So we can plug this in. Negative 2.18 times 10 to the negative 18, 1 over 3. Nope, 1 over 1 squared minus 1 over 3 squared, sorry. So when you plug this into your calculator, you get negative 1.94 times 10 to the negative 18 joules. This is delta E. Delta E is negative. It is emitting energy as light with a wavelength of E photon equal to negative delta E. So delta E equals negative E photon. And so we have been asked to determine the wavelength. The energy of a photon is Planck's constant times the frequency. The speed of light is equal to the wavelength times the frequency. We can rearrange these constants algebraically to where the speed of light divided by the wavelength is equal to the frequency. So E photon is equal to hc over lambda. We've been asked to determine the wavelength of light. I'm going to re-isolate this equation where the wavelength of light is equal to Planck's constant times the speed of light divided by delta E, which in this case is a negative. It is negative because E photon, which is what we've put into here, is for a emission is negative delta E. From here, we're going to start plugging in values. The wavelength of light is equal to 6.626 times 10 to the negative 34th joule seconds times the speed of light, 2.998 times 10 to the 8 meters per second, divided by negative 1.94 times 10 to the negative 18 joules. This gives us 1.02 times 10 to the negative 7 meters. And 1 meter is 1 times 10 to the 9 nanometers. So our final answer is 102 nanometers. While this question doesn't indicate it, the number of significant figures expected will be provided in the question. Or you cannot lose points because there are no sig figs in the problem. I'm going to give you guys 30 seconds to marinate, then I will take questions.
would we want, what is like the default state, right?
So n equals 1 is the ground state. So if it doesn't have to equal 1. It will often not equal 1. So basically, if you have an incomplete transition, or in certain materials, the emissions are in certain sets. So you don't always fall from the highest rung to the ground. Sometimes it can make lateral or shorter transitions.
It's negative 1.94 because it's divided by negative delta E. And it's 1.94
Yes.
negative, so it's, okay.
Where did you get the negative delta E? Wouldn't it just be delta E?
So if you moved this negative sign here, you don't need it there.
Okay.
That is for clarity, although if it's unclear, I tend to move the negative sign here and then just don't bring it over.
Okay.
So you don't need to show that. This is so that when you look back at your notes, you're like, I know what she was talking about.
Can you explain how you got the formula?
The formula at the top? Yeah. So we know that E photon equals Planck's constant times the frequency, right? We also know that the speed of light equals the wavelength of light times the frequency. Algebraically, we know if you isolate frequency, it is the speed of light divided by the wavelength. So I plugged that into this equation. So E photon equals Planck's constant times the speed of light divided by the wavelength. We are solving for the wavelength. I like to move constants around because it's less writing. That's a me choice. You are not required to choose this. So I rewrote this where delta E equals negative E photon. So this equation came from the transformation of HC over lambda equals E photon. And E photon equals negative delta E. So I put HC over E photon equals lambda. So in algebra, you can move around equations. The alternative method, which I will not write on the board because I'll be here for 10 days, would be to take delta E, solve for the frequency. Using the frequency, you can plug it into the speed of light and solve for the wavelength. But if it is set up like this, where it just gives you the transition and asks for the wavelength, you can get there from delta E to E photon to the frequency to the wavelength. I just did all of the equation manipulation as constants and variables because you can do more of that easily. Other questions? Okay. Using this as a basis, please repeat this. All of you should write something, even if all you know is NF and NI. Yeah.
Is EPH, is that always gonna, I mean, is the delta E always gonna be negative EPH?
Only if it's emission. So on this one, where it's absorption, so if it goes up, no.
Okay, gotcha.
So it is a way, if you were to have plugged in the negative value, you would have gotten your wavelength is negative 102 nanometers. And that's not a thing.
So
So the wavelength has to be positive. Which is why the Rydberg equation doesn't always work. Because it only works sometimes. And this will get you the right answer all of the time. This is 1. Well, so if it starts at 3, it ends up. Those are kind of janky lines. They don't look as good as the one over there. They're not spaced correctly. I realized that after I hit publish, so that's one. Yeah, so H is one constant. And that H and C are on your equation sheet. I think you did those. Is that in your exercise? It's 1 over 25 minus 1 over 9. That's why. So in this case, Ni equals 3. And equals 5. And so delta E equals negative 2.18 times 10 to the negative 18 joules. 1 over 5 squared minus 1 over 3 squared. In this case, delta E is 1.55 times 10 to the negative 19 joules. This is absorption. So delta E equals E photon. So we're going to similarly manipulate the equations as shown on the other side, where the wavelength of light is Planck's constant multiplied by C over E photons over delta E. It needs to be in nanometers. So in this case, once you plug all that in, you should get 1281 nanometers. Alternatively, I would have also accepted 1280 with 3 or some version of that using scientific notation. So the way you assign the states is you count up 1 in each line. Yeah.
I got the same thing for delta E, but I don't know what I did because I got a completely different answer when I put it in nanometers.
What did you get?
I have negative 427.
And you got 1.55 times 10 to the 19th joules.
Yeah.
Did anyone else get 400 and something? Did anyone else plug it in their calculator? Did anyone? Did you get 4?
No, I got 128 or 120,
I got where you were going with that. I'm trying to see if I can think of where you added something wrong.
Yeah.
I don't know. Mostly because you didn't do any of the mistakes I had previously thought you might have done if you got 1.55. Yeah.
Why is the delta E, why is that not negative?
I just erased that. But if you scroll back in your notes, like, or flip back, the delta E equals E photon in the case of absorption, which is where the arrow points up. Basically, the short answer is if it's negative, if delta E is negative, you have to get rid of the negative in order to determine the wavelength. So if it is positive, then you don't have to do anything with that number. That's basically what that means.
So the one that you were on was the like delta E equals negative E photon. The reason why it's like negative E photon is because it's going down, right?
Yes.
This question is going to be positive.
Yes, so when it absorbs energy, the energy going into the system is equal to the energy of the photon.
Okay. And also, why do you have like a negative and negative control at the time of research? First, so like it's negative from C negative 1.9 or 4.
So delta E equals negative E photon. You can bring that with you or move it out, mostly trying to show that that's where the negative sign went. Couple of math is hard moments. For whatever reason, 3 squared is more often than not 6 in our brains, where we know that 4 squared is 16. Just as a note, that is what can often happen in our brains. So 3 squared is in fact 9. What you got?
So if we start with this kind of equation or question, would it always be that kind of equation? Is that something that would be standard if we're being asked for the wavelength?
I would not. I mean, you can memorize that equation, but that makes the assumption that I'm always asking you for the wavelength. Because it's possible that I ask you for other data. And if you memorize that equation, it helps. But what happens if I don't ask you for the wavelength? Will you be able to isolate something else other than just the wavelength? Because what if I gave you the wavelength? Or some other insane atom?
Whenever I plug it into my calculator, I get 128 instead of 1280. Is it just like I'm doing something wrong with the calculator?
It may be that you're putting in the nanometers slightly wrong. That would be my guess. Because I did it twice to make sure that this was the right number. I would double check that. Other questions about this calculation? There will be one, at least one, like this on mini exam 4. Does anyone need me to say that again? Do you want to star this on your notebooks? I'm definitely going to ask about this. It's probably going to be one of those, like, I don't know, 12 to 14 point problems, many calculations. It will probably be in nanometers. It will tell you how many significant figures you need.
Is there an easy way to make sure that the exponents add up when you do the calculation? Because when I do it on my calculator, every single time the exponents go up.
Yes. My guess is that you are starting. Yes. Let's, after class, I'll show you how to use it. I don't want to say how to use your calculator right, because that's super mean. But let me show you the way that I use the calculators, because maybe that will help you. Because my guess is, previously, we only ever used one exponent number. And however you're putting them in, you don't have enough parentheses in order for it not to just like start doing weird fake math things. So if any of the rest of you are having calculating, like you get the right number, but you're off by many, many exponents, feel free to come down at the end, and we'll all have a slightly short, here's how you use your calculator chat. Because exponents on exponents on exponents is hard. So there are tricks to that, and I'm happy to help out. Great question. Thank you for asking. Any other questions? So the Bohr model. The Bohr model is this. These calculations are how we use the Bohr model. So the Bohr model is that model that says electrons exist in discrete states, they can transition between them, and they do not, in fact, collapse into the nucleus. That's the Bohr model. So the limitations of this model are pretty substantial. One, this model works really well for hydrogen. How many electrons does hydrogen have? How many other elements only have one? Zilch. So it turned out, because it was designed with one electron, it works. These same transitions between one and the other, as soon as you have more electrons, get way more complicated. So the Bohr model basically collapses or is not as accurate as soon as you have more than one electron. I don't want to say 100% of electrons, because that's 119 minus 1 over 119. So what, 99.9% of elements have more than one electron? So the Bohr model is super good, but not accurate for the majority of elements. So this was really informative because it tells us that our elements, our electrons exist in discrete states. It tells us they are in specific places, and that they can involve in a transition between one and the other. All of this is to tell us we see these electrons, and then we can kind of think about what they do. So in 1929, the Nobel Prize was awarded to Louis de Broglie for the wave behavior of matter. All matter, when moving, has a wavelength. This wavelength is either too big or too small for us to see. If I were to throw a baseball or anything else, it would have a wavelength. It turns out that any curved line, if you look at a really small segment of that, doesn't look curved. We can go into the weird physics of that later. So the de Broglie equation is Planck's constant divided by the mass in kilograms multiplied by the velocity. This equation allows us to think about the wavelength that an electron has around the nucleus. The wavelength is essentially the size of the atom. So basically, the electron wiggles around this nucleus, and it has some wavelength. So the de Broglie equation tells us that these electrons have a wavelength as they move around. This is an informative equation. You will not be using it on a mini exam. You will not be using it on Alex. You will not be asked to solve this calculation in my class at all. Any questions? Do you need to practice using this? No. Excellent. We are all on board. So in 1932, the Heisenberg is awarded the Nobel Prize for the uncertainty principle. So in the late 1920s, early 30s, they were trying to understand, so we know the electron is moving. We know it has a wavelength. So once something has a wavelength, it kind of implies that it has wave behavior. We live in Florida. We know what waves look like. Kind of move around. They oscillate back and forth. And we know that there is a difference if I squirt you with a wave gun versus a water gun. One involves like a lot more water, but same death. So the reality is a particle and a wave are two discrete entities. And so they were trying to understand how an electron behaves. So if you have an electron apparatus or an electron gun, and you shoot it at a wall with two apertures, so it has two holes in it, it's called the double slit experiment. And so if you put a detector back here, we can see a couple of things. So this is what a wave would look like, where you see these radiating peaks. So if a wave of water came in and you detected where it hit, the waves would interact with each other. And so this has what we're going to say, no detector. So this tells us that we have a wave behavior. Super cool. So was, what they wanted to know next was, well, we are shooting one electron at a time, and we detect one electron at a time, but we're seeing these wave behaviors. So they said, I want to watch. Where does the electron go? So they're gonna, I don't really know how to draw a detector, so it looks like a weird, creepy eyeball. We'll have to cope with that. So now we have an eyeball, and they're gonna watch. They wanna know, where does the electron go? We're gonna use same setup. Now we have a detector. And what we see is particle behavior. So if you were to shoot, if I were to throw tennis balls at a wall, eventually what you would see is they either go through the aperture or they don't. Aperture meaning hole. So they either go through and hit the wall or they don't. And there's a little bit of wiggling if it maybe, I don't know, if I have super skills and it slides a little to the left or the right. But you don't really expect to start seeing these wave interference patterns like we do here. In the absence of a detector, we see a wave. With a detector, we see a particle. Many of you now have a burning question, but why? We do not know. We know this to be true. This has been replicated many, many times. It is well documented that when the detector is here, you get particle behavior. When there's no detector, you get wave behavior. And so there's still ongoing research. There may be more insights than I am aware of. But this tells us that we have two different data points. We can know where the electron is or how fast it is going. So the Heisenberg uncertainty principle, delta x is change in position. Delta mv is the change in basically velocity. And so you could either know where it is or how fast it's going. This equation is also more of a, I'll call it an interesting fact. This helps us figure out where the electron is and why we want to know where it is. Because is it a particle or a wave? And how does that affect its behavior around the nucleus? What questions do we have other than why? Why is a valid question? That means that you like science. I just don't have any good answers for you.
What is the detector like made out of? How does it operate?
That detector detects the presence of electrons. They have done this whether you use different detectors, they've used optical detectors, they've used electric detectors.
How do they detect electrons?
I have no idea. Now that you ask that, I have no idea. In my mind, I frankly always picture like a speed gun, like, you know, if you're speeding down the highway, and that's what I imagine. Which is probably not what it is. But if it was the effect of the detector, which is what you're hypothesizing, it turns out that if you spread these, the detector should only affect this, so you should see a wave behavior and a particle if it was due to the detector. It is true that you see only particle behavior when the detector is on. It is not due to the detector. Because they've done some interesting, is the detector on, is it off? There's a whole lot of weird stuff. I can send me an email, I'll send you some like videos that I think are interesting, but are way outside the scope of what we're talking about here. This is more of a like, fun fact, make your brain hurt, then we're gonna make it not hurt this bad. Other questions?
So the wavelengths like get bigger where the aperture is? Like where both apertures are?
This?
Yeah.
We live in Florida. If you have a channel where the waves go through, what you get is like a rippling effect based on the size of the channel and how big the waves are. This is, if you were to stick like a piece of paper in there, that's what that is. So in the front of the channel, you get the most waves, and then it basically ripples out. That's what that very hard drawing of that is supposed to be. We've seen my art skills there. Subpar at best. Any other questions? So for the remaining 30 minutes, we're going to talk about quantum numbers. Quantum numbers, also like last class, and we are not going to finish. Chapter 6 is 3 distinct packets of info that all tie together with where on Earth are the electrons in any given element. We're still not going to get all the way to the end, so we now have been able to say we have electrons. We're about to figure out where they are. We are going to stop in a place where you will still want more information. That's okay. But we're going to make it to the point where we can talk about how you will be, I don't want to say quiz because I don't like that word, how you will be tested upon your knowledge on Monday. So at the end of this section, there are not example questions, but plausible example questions from like mini exam type things, if that makes sense. Of course it makes sense. So, quantum mechanics and atomic orbitals. So we know roughly where the electron is. It is around the nucleus. But what they're figuring out and what we're learning is it's not just around the nucleus, it's around the nucleus in different layers and positions, and what we're soon going to meet are orbitals. So in 1926, Schrödinger proposes his famous equation. So Schrodinger's equation is deceptively simple. It is H psi equals E psi, where psi, this pitchfork thing, is a wave function. These are complex, multidimensional equations that give insight into the location of the electron. So you can't just cancel the two pitchforks out and say H equals E, which would be super cool, but that would definitely not be an equation. So in these calculations, he's trying to say, how can I give the electron an address? If I want to mail you a holiday card, I cannot just say, send it to Avni. I cannot just put her first name on the line and just hope that it gets to your house. That only works for children and Santa, right? And I don't even know where those go. They go somewhere. That's what that works. If you want to send me a holiday card, you cannot just write Dr. Malcolm and drop it in the mail and hope for the best. You might get there with Dr. Malcolm and UNF, maybe, and a stamp. But the reality is, if you wanted to mail me a holiday card or something else, you have to send a full address. Now, at the risk of making myself sound like I'm 912 years old, when you address like letter mail, it is a name, followed by a street address, which includes a number and a street, followed by a city, a state, and a zip code. In case you've never actually addressed a card, since most people, I just email my mom now. I don't mail her anything. But that's how you would get a card, or that's how you would send a card. So in this case, we are trying to ask this question. What information do we need to give our electron an address? So he started with it's called the particle in a box. He basically made the atom a line. And he makes this line, and he says, okay, if we have the n equals 1 shell, the electron could be anywhere in this line, and it doesn't have any nodes. For n equals 2, we're going to have a singular node, and it's going to change the dynamics. Now, I am not musically inclined. Maybe you are. If you play a stringed instrument, it is my understanding that you can change the tone and the pitch of the sound by changing the length of the string. Give or take, that's how this works. When you do that, you basically shortened or lengthened the amount of string that is allowed to oscillate. Where you put your finger, or the clampy thing, or whatever else it is in any of these other instruments, I'm really not musically inclined, I just watch TV. Whatever you do, it changes the length of that. When you pluck the string, or however strings get moved, it oscillates up and down, and it changes the pitch. So these particles in a box basically say the electron moves back and forth in this pattern. But really for this, it's going to oscillate around this node. A node is where the electron cannot be. And so these quantum mechanics in the atomic orbitals give us insight into where on Earth the electron could be. So the wave function is super important, but all by itself, it's kind of meaningless. It is a complex equation that in the right apparatuses or calculations gives a lot of details. But it turns out that the square of that, so psi squared, gives you a probability density. So psi gives you like this abstract concept. Psi squared says, yeah, I think we're pretty sure that the electron could be in here, which is great news. We want to know where it could be. And so at the, not the end, momentarily, we will look at what the orbitals look like in 3D space. And so psi squared basically says, hey, we think that some orbitals are spheres and some are other shapes. So how do we think about the location? We need a state, a city, a street, and a house number. Those are the address points that we're going to get for these electrons. So there are 4 quantum numbers. We're going to talk about N, L, and M sub L first. So N is the principal quantum number. So its allowed values are n equals 1, 2, 3, all the way up to infinity. So it could be any whole number, the same as those lines that we saw in the delta E calculation. So the allowed values are this. And so n increases, or as n increases the distance from the nucleus increases. So this is what's called the shell. And we can think about this as the state. So if I tell you that my favorite place to get tacos is on Main Street, you don't know where that might be. If I tell you that my favorite place to get tacos is in Dallas, Texas, or even in Texas, you know where, you have the general idea of where that might be. So we have a state, and this is the shell. So if we look at our graphic, we can see that n equals 1 is closest to the green nucleus, 2, 3, and 4 are increasingly further apart from the nucleus. And they are all circularly around the nucleus. So the angular quantum number, or angular momentum, L, this is going to be our subshell, or the orbital, otherwise known as the city. And so the angular momentum, the allowed values are 0 all the way up to n minus 1. And so in this case, it defines the type of the orbital. So when L equals 0, we have an s orbital. When L equals 1, it is a p orbital. L equals 2, as well as L equals 3. You will need to have acquired this table of knowledge. I don't want to say memorized. It's less than memorized, like somewhere between learn and memorize. You will need to know that a d orbital is in the L equals 2 value.
The orbitals that will be for
we will not get there today because life seems to be slow in my brain. But where we are going is where in other chemistry courses, they say, like, these electrons, you have the 1s2, 2s2. We are spending 2 days deriving where that information comes from and how that fits with quantum numbers. So on Monday, all this comes together in 5 days with a beautiful package. Good question. Other questions? So the next one is the magnetic quantum number, m sub L. And so the allowed values are negative L through 0 all the way to positive L. And so this tells you the direction or the number of subshells within any subshell. So these are the suborbitals. So let's call these just orbitals. Somebody just went out, right? Sorry, I thought someone was banging on the door because I didn't see them, and I was like, I got what's happening. We'll call the city the orbital, and these will be the suborbitals. And so this would be the street. And so together, these tell us information. Yes?
Are the allowed values continuous or discrete?
What do you mean by that?
Like, can we have like 0.2, 3, 4, 5?
No, they are whole numbers. All of these are whole numbers. That's a fair question. So the values are negative L through 0 to L. So for L equals 2, it would be negative 2, negative 1, 0, positive 1, positive 2. So we're going to go back to, in your notes, you probably want to quickly sketch something that looks like this, because I'm going to draw on it. You could do it on the bottom of this page, or in basically any of these subspaces, because we're going to talk about how these fit together. For n equals 1, the allowed values of L is 0 up to n minus 1, so that would be 1, or 0. So we have L equals 0. When L equals 0, the allowed m sub L values are just 0. Oops. For the n equals 2 shell, there are allowed values of 0 and 1. Within L equals 0, the only allowed values for m sub L is also 0. For m sub L for L, it equals negative 1, 0, and 1. And that's in the n equals 2. So we could basically say that there are 3 discrete entities in here. For n equals 3, we still have L equals 0, where m sub L equals 0. L equals 1, with m sub L equals 1, 0, negative 1. We also have an allowed value of L equals 2. So the m sub L possible values are from negative 2 through 0, positive 2. So we have negative 2, negative 1, 0, 1, and 2. And that's in the n equals 3. What you can see is that as you increase n, you see more and more L values are allowed. Within each L, there are suborbitals. So in L equals 0, there's only one option. So together, these tell us where we can find the electron. If I say it's in n equals 2, you know it's here. L equals 1 is here. L equals 0 means it's in one of these boxes. These are just different ways that we can address where the electron is. So one thing we know is that N means they're in a specific shell. You can think about this like onion layers. Or if you go to somewhere cold, like different layers of your outfit. You have the outer layer, the next layer, the next layer, the next layer. So as you get further away from the nucleus, there are more options for you to sit. That is true in this classroom-ish. The front row has less seats than some of the further back rows due to space. Although actually it doesn't look that way at all, so you can just kind of delete that statement from your brain. But any subshell contains the electrons for N and L. So these quantum numbers, N has N subshells. So N equals 5 has 5 different L values. Each subshell has a specific number of orbitals, 2L plus 1, which is also negative L to positive L. And the total number of orbitals in a given shell is N equals 2. So what does an S orbital, a P orbital, a D orbital, and an F orbital look like? So it turns out that the psi squared functions for an S orbital look like those blue speckled dots on the left side. It basically says, if you take enough pictures over time, you get it's mostly circular. So I could ask you to draw an S orbital. If you were asked to draw an S orbital, you would draw a circle. If you don't know how to draw a circle, it's just like a round thing. That didn't help you at all, but you get where I'm going. Right? So if I said, draw the 5s orbital, you would say, I draw a circle with some Cartesian coordinates. Those are basically the lines that give you 3D perspective. So this is the 5s. But any s orbital will look the exact same because they're round. Right? We all feel confident in our ability to draw an s orbital? Maybe, hopefully. So the p orbitals. P orbitals are when L equals 1. When L equals 1, M sub L equals negative 1, 0, and positive 1. There are 3 p orbitals. Those 3 p orbitals are in 3D space on the x, y, or z axis. They look like dumbbells, as you can see over here. Now, I'm wretched at drawing. We're all on board with that. If I ask you to draw the p, y orbital, we have an x, we have the y-axis. It looks like this. You have an orbital on the y-axis. The x orbital will go here. No lie, if I am asked to draw the z orbital, I just like put the z in the plane of the paper. You can draw it in 3D space if that's your jam. That's not my jam. Just rotate the axes. So you can draw any of these orbitals as well. So the s orbital is L equals 0. It only has one choice. At L equals 1, there are 3 options. Those 3 options for your electron are the x, y, and the z axis. The d and the f orbitals. I feel like I made a big thing about like you could draw these. You cannot draw these. D's and f's are hard to draw. So I'm going to ask you to draw, it's these. It will not be those. All right, good. So the d orbitals, there are 5 d orbitals. And they are given annotations like dy squared, dxy, dyz. The yz or the xy or the z squared tells you where it's located. It's like an extra address. You live on Main Street, the 3rd. I don't know. Doesn't really fall apart. For f orbitals, there are 7 unique f orbitals. An f orbital is L equals 3, which is negative 3 to positive 3 through 0. So the way that these look, we know that the electrons are going to fit in any one of these. So it turns out that all elements, aside from hydrogen, have more than one electron. I know. So where do the multiple electrons live? If you and someone share a home, two people live at the same address. Both of you can get mail there, right? But you cannot, this gets a little wonky, occupy the same space. If one of you is standing here, the other person, you can, that's just weird, you're standing on someone. So it falls a little bit apart depending on how you like your personal space. But one of you can stand here and the other can stand next to you, but the two of you cannot occupy the same physical, singular spot. So the question becomes, in these orbitals that we're thinking about, how do we deal with the fact that we need to give an address that distinguishes between two electrons? So it's really important to note any orbital, well, all orbitals contain two electrons. So the 1s orbital contains two, or can seat two electrons. I like to think of them as little tables. Each little orbital can have two little electrons that hang out in there. We need a way to tell them apart. And we are going to use our very last quantum number, m sub s, which is the magnetic spin quantum number, to tell these two apart. And so it uses the Pauli exclusion principle. So Pauli says no two electrons can have the same four quantum numbers. So we distinguish them using the magnetic spin, where ms equals +1/2 or -1/2. Each electron, or each orbital, can contain two electrons. So if we go back here, we have n equals 1, L equals 1, m sub L equals 0, but two electrons could live in this box. And we need a way to distinguish them from one another. So arbitrarily, in Jenkin 1, we distinguish them as +1/2 or -1/2. If you have seen electron configurations, and if you haven't, we're going to talk about it on Monday, where we draw the line with the two arrows, one going up and one going down. This up and down, that mechanism is how we distinguish between the two of them. Each little line or suborbital can contain two electrons. Those two electrons, one is positive, one is negative. So now we've met all four quantum numbers. Any electron has four quantum numbers. Then we can assign those four quantum numbers. So I'm going to write over here on the board that the online people cannot see. Sorry, online people. So if there's N, L, M sub L, and M sub S, we are going to look at the 3D, and nope, that's P. I'm going to make this the 3px, the 4D, x, what is that, 5s. So in this case, the 3p tells us where the electron is. And I'm asking, where is the electron? Give me the four quantum numbers that correspond to that. So quantum number questions come in three flavors. One, a multiple choice question that asks, which of these is wrong? We've never had a multiple choice question, so that's not happening. Two, it asks, give me the 4 quantum numbers for an electron in this place. That's probably, not probably, you will definitely be asked to do this. So this big number here is the principal quantum number for any of these type of values. So n equals 3. The next value, S, D, or P, tells you the L value. So based on the chart that I didn't write all of, but it's a couple of slides back that you need to know, a p orbital is always L equals 1. Now, there are not many choose your own adventures in Gen Chem 1. This is really the only one. But for the purposes of this class, we cannot distinguish between the 3 orbitals. If Gen Chem 1 really jazzes you want to hang out with us for the rest of your career, in physical chemistry, like many courses from now, you will learn that specific quantum numbers correspond to specific orbitals. That's way outside the scope of this class. So what you need to do is you need to choose one allowed value for an M sub L orbital. I'm feeling positive because I'm positive that I'm getting a snack after this. Plus 1, because the allowed values are L, negative L through 0, positive L. And M sub S equals, in this case, I'm still happy, plus 1/2. So for these two, you pick any allowed value. Any one you like, as long as it's allowed. If I say you may have a cookie, you may only have 1 cookie. Any means 1. I'm not asking for a list of all of them, I want 1. So for the 4dxy, n equals 4, L equals 2, M sub L, what are the allowed values based on L for M sub L? Negative 2 through 0 to 2, so we'll feel sad, will be negative 2. M sub S, I just need n allowed value. Since we were previously negative, I'll choose to be positive 1/2. Questions about these?
So what does the P, and because you said for the first one, the P is always 1. For the D, how do we know what number it is?
It's always 2. So on this slide, these are the these are the values. So in the n equals 12 shell, you could have L values of 1 to 11. We just have yet to detect orbitals past the D and F orbitals. So for this last one, for the 5s, n equals 5, L equals 0. In this case, M sub L equals 0, and M sub S can be either plus 1/2 or minus 1/2. I will again choose plus 1/2. So the other types of questions that you can expect to see. Yeah. Why is L 0? Yeah, so the s orbitals are always L equals 0. That I don't like just because, but for L values, they are one of the rare times where that is the answer. So any s orbital, whether it's an n equals 1 or n equals 100, the L value for an s orbital is 0. So for these, we're going to start with the second one, then go to the top one, then go to the last one. So what is the designation for the subshell n equals 5, L equals 1? It's the 5p. So you would write, I don't know, a normal size 5 with a P next to it. So if these would be AEC, it would be a 5P. So for any N and L combination, you should be able to determine whether they are S, P, D, or F, provided the L values are between 0 and 3. So the second one says, an orbital has N equals 4, and M sub L equals 1. What are the possible L values? If we can only see N equals, we'll look at N equals 3. We know that M sub L is plus 1. So we only see plus 1 in L values greater than 1. So the allowed values would be L equals 1, 2, or 3. Because M sub L values are anywhere, or M sub L is negative L to positive L. So if M sub L equals 1, L cannot equal 0. It can be anything else. I promise this is not as complicated as we're all feeling like it is. And the last one asks, how many orbitals are in the N equals 4 shell? So the number of orbitals is N squared. So it's just 16. That is the end of the quantum numbers. We will talk more about those on Monday. It will be not on the mini exam, but it will give additional clarity. Does that make sense? We will solve more examples, is what I'm attempting to say. This is on the mini exam. So 6.4 uses all of this information, so we'll continue to discuss it, but you could do examples. You should expect this, or any combination of that on the mini exam on Monday. That it is this, or it tells you that it is here. But for that specific question, it doesn't really make a difference. It doesn't matter to you. That sounds sick. To us in Gen Chem 1, it doesn't tell us anything. If you spend a lot of time thinking about orbitals, it does. It tells you that it is a specific M sub L. In Gen Chem 1, we're like just learning these things. So all I need you to do is pick N allowed value. You could put M sub L equals 0 100% of the time, and it will always be right.